The Moon, Earth's only natural satellite, has fascinated humanity for millennia. Its origin is a topic of significant scientific investigation and debate, with theories evolving over centuries as our understanding of planetary science has deepened. This essay explores the prevailing theories of the Moon's formation, evidence supporting these theories, and the broader implications for planetary science. Before the advent of modern science, the origin of the Moon was shrouded in myth and speculation. Ancient civilizations often attributed its existence to divine or supernatural forces. With the rise of astronomy as a scientific discipline, hypotheses about the Moon's formation began to emerge based on observable phenomena. By the 19th and early 20th centuries, three primary hypotheses dominated scientific thought. The fission hypothesis, proposed by George Darwin, son of Charles Darwin, suggested that the Moon was once part of the Earth. According to this hypothesis, a rapid spin caused a chunk of Earth's material to separate and form the Moon. The Pacific Ocean basin was thought to be the remnant of this event. The capture hypothesis posited that the Moon formed independently in the solar system and was later captured by Earth's gravitational pull. This idea struggled to explain how such a large body could be captured without a significant alteration in its orbit. The co-accretion hypothesis suggested that the Earth and Moon formed simultaneously from the same primordial disk of gas and dust. While this theory accounted for the proximity and shared material of the two bodies, it failed to explain differences in their compositions. Today, the most widely accepted explanation for the Moon's origin is the giant impact hypothesis. This theory posits that the Moon formed from the debris generated by a colossal collision between the early Earth and a Mars-sized body, often referred to as Theia. This impact is thought to have occurred approximately 4.5 billion years ago, shortly after the formation of the solar system. The collision would have been energetic enough to vaporize a significant portion of both Earth and Theia. The resulting debris formed a disk of molten and vaporized rock around Earth. Over time, the debris coalesced due to gravitational forces, eventually forming the Moon. The newly formed Moon began in a closer orbit to Earth and has since migrated outward due to tidal interactions. Several lines of evidence support the giant impact hypothesis. Earth and Moon rocks share remarkably similar isotopic compositions, suggesting a common origin. This is consistent with the idea that the Moon formed from Earth's material. The Earth-Moon system's angular momentum is consistent with the aftermath of a giant impact. Advances in computational modeling have shown that a giant impact can produce a Moon-sized body with characteristics similar to our Moon. Moon rocks brought back by the Apollo missions reveal a lack of volatile compounds, consistent with a high-energy impact scenario. While the giant impact hypothesis remains the leading theory, it is not without challenges. For example, the similarity in isotopic compositions between Earth and the Moon is more pronounced than some versions of the hypothesis initially predicted. This has led to refinements and alternative ideas, including multiple impacts. Some scientists propose that the Moon may have formed from the debris of several smaller impacts rather than a single colossal event. The synestia hypothesis suggests that the impact created a synestia, a donut-shaped cloud of vaporized rock, from which the Moon eventually condensed. Recent studies suggest that Theia's composition may have been more similar to Earth's, which could explain the isotopic similarities. Our understanding of the Moon's origin has been profoundly shaped by lunar exploration. The Apollo missions of the 1960s and 1970s provided invaluable samples and data that have been instrumental in testing theories of lunar formation. More recent missions, such as NASA's Lunar Reconnaissance Orbiter and China's Chang'e program, continue to provide insights into the Moon's composition, geology, and history. Lunar exploration has revealed that the Moon's crust is rich in anorthosite, a rock type that reflects the Moon's early history as a magma ocean. This supports the idea that the Moon underwent significant heating and differentiation after its formation, consistent with the giant impact hypothesis. The study of the Moon's origin has implications far beyond our own satellite. It sheds light on the processes of planetary formation and the dynamics of early solar system evolution. The giant impact hypothesis, for example, underscores the role of catastrophic collisions in shaping planetary systems. Additionally, Understanding the moon's history helps scientists infer the conditions of the early Earth, including the development of its atmosphere and the emergence of life. The moon's stabilizing influence on Earth's axial tilt may have been crucial for maintaining a climate conducive to life. Despite significant progress, many questions about the moon's origin remain. For instance, why are Earth and Moon isotopes so similar? Some theories suggest that Theia was compositionally similar to Earth, while others propose extensive mixing of materials during the impact. What was Theia's fate? While much of Theia's material likely merged with Earth and the Moon, the exact details remain unclear. Could other processes have contributed? While the giant impact hypothesis is compelling, it may not tell the whole story. Future research may uncover additional mechanisms at play. The origin of the Moon is a captivating story of cosmic collisions, planetary evolution, and scientific discovery. From ancient myths to modern simulations, humanity's quest to understand our celestial neighbor reflects our enduring curiosity about the universe. As lunar exploration continues and scientific techniques advance, we can expect to learn even more about the Moon's mysterious beginnings and its profound connection to our own planet.